I want to go to Mark Sokol. And Mark actually has, and where did my window go? He actually has Kieth with him, Kieth Earle. So Mark is going to be doing updates. He has Associate Professor and Chair of Physics, Kieth Earle with him, who's going to be talking about basically EPR. Dr. Earle works with Kevin Newth and Matthew Sidagas at the University of Albany. So he is not part of the SU, but they will be joining us. Mark, can I hand things over to you, sir?
Yeah, sure. We're ready to take things on over here. It's actually great that things are moving a little ahead of schedule.
Yeah.
We were hoping to be able to have some free time to get some machining going on over here at the lab. So we are joined by Professor Kieth Earle of the University of Albany. He's also logged into the Zoom call from a separate login, so he'll be able to do a little presentation. Professor, you want to introduce yourself?
Sure. My background is in electron paramagnetic resonance, which is related to a class of spectroscopies that is very much a part of the Alzofon experiments written up by Alzofon and commented on by his son. And so I've been in the area for a number of reasons, but I've been reminding myself about dynamic nuclear orientation, and I'm helping Mark leverage my expertise in electron paramagnetic resonance to help him to develop what I'll call a vanilla EPR spectrometer, which can then be tweaked in cruel and unusual ways to do some dynamic nuclear orientation experiments with the hopes of repeating some of the experiments that have already been done.
So this was the waveguide that we had going on in the beginning, and too bad we weren't in contact with you at the time that we designed it, because we learned that this is not the right dimension of a waveguide in the X-band, right?
Yeah, no, that is a big resonator, but it's a little too big for X-band purposes. So one of the enjoyable tasks that I've had while here is to help Mark converge on a set of more appropriate parameters, and we're making little ones out of big ones, taking sheets of metal and putting them together into a good cavity structure that will be useful for an EPR experiment. And then, as I said, the idea is to see something, and then once you see something, you can tweak it to look for other effects. So that's the goal.
Such as dynamic nuclear orientation, right?
That's right. That's right.
And we also came up with these dimensions over here. This is the TE102, right?
Yep.
The TE102 design, and that's pretty much like the standard waveguide size for X-band. And the samples that we made for most of these experiments are going to have to be trimmed down a lot. Like, we're talking about samples that are probably about this big is the max that you'll be able to stick inside that chamber.
Yeah.
Right.
Well, we'll see. But yeah, that's certainly characteristic of the size of a lot of EPR samples. So my contribution today is I'm going to present some slides from a talk that I gave a while ago to try to give folks a feeling for some of the considerations that go into an EPR experiment. And so this is going to be an interesting mix of theory and experiment, and will perhaps help members of this community appreciate where I'm coming from. And I'm hopeful that some of the insights that you can share with me will help me be a more effective advocate for what Mark is trying to do.
Okay. I think if you want to do the slides, we're going to have to transfer over to.
Right. So I guess if you could allow me to share screen.
Yeah, he's under Kieth Earle, man with the bagpipes.
Right. And so let me run this as a presentation. If the, or a slideshow, if the EPR gods are kind. So as you can see, this presentation is a little long in the tooth, but it does have some features that are relevant to this discussion. And so what I'm going to be talking about are some of the ingredients that go into defining what an EPR spectrum is and some of the physical effects that can affect what that spectrum looks like. And along the way, I'm going to introduce some tools. So this is really what I'll call a toolkit talk. I'm going to open up the EPR spectroscopist toolkit, show you some of the toys that we have at our disposal, and then solicit your input for how they might be usefully applied to the Alzofon experiment. So to give you a little bit of background on what I do, a lot of my interest has been in studying dynamic modes of proteins. And what you see here, can you see the arrow moving around on the screen?
I believe they can, because this is the,
Yeah.
yeah,
So
they
I'm
can't see it.
gonna assume yes. And so this is a protein, T4 lysozyme, that's commonly found in tears, for example. And its job is to go around and attack bacterial infections. So you can think of it as operating kind of like a pair of psychotic barber shears, just going around in your tears and attacking bacteria and rendering them harmless from our perspective. And so this by itself is not something that you can actually see in a magnetic resonance spectrometer. And so what you can see is something that has an unpaired electron on it that's functioning rather like a compass needle. And such a thing can be seen on this nitroxide moiety. This dot is an unpaired electron that resides on this single NO bond. And as you can see, it's attached to a chemical moiety, which itself is attached by a tail to the protein. So as you can see, if this is what's being observed experimentally, and we're trying to get information about what's going on in this protein, and then the connections are in fact rather indirect. And so I'm going to risk something and try to play a video. So I'm going to stop sharing and attempt to share something else. Let me bail out of here and try to show this. Go back to here. Share screen.
Oh, there you got it. Right, showing up.
And make it real big and let it run. And so what I want you to focus on is the shaking of this. This is the nitroxide moiety that we've attached to this protein, and you can see the modes moving, and you can also see a little bit of movement on the protein, but as you can see, most of the shaking is going on here. And this drives home the point that in EPR spectroscopy, at least in these biological systems, we only have indirect information that's readily available. So what I'd like to do now is bail out of this, go back to my presentation. Assuming I can find it. There we go. And I have to say I am shocked, absolutely shocked that this is running as smoothly as it is. I had no reason to hope that this would be the case, but in any event. So one of the things that we do as spectroscopists is proceed by analogy. So I hope that one of the things that the video made clear is that there are a lot of different time scales that are relevant for a complete description of what's going on. And in many ways, it's similar to the parable of the blind monks. Many blind monks, pooling their knowledge, can learn a lot about the elephant. So for instance, this monk is experiencing the rapid motions of the elephant's tail, and that might correspond to one of the modes of the EPR active moiety moving about rapidly in solution, but it's attached to a much larger object, the elephant. And as you can see, this monk is perhaps more sensitive to slow overall global tumbling of the elephant. And there are other monks, such as this one, who are completely out of the picture, knocked away. They are sensing motions that are not directly correlated with the elephant and can't contribute much to the discussion. And so what we have here is we need to develop a level of description that's appropriate for understanding what's going on with the modes that are of interest. So I'm going to stop sharing and try to share another brief video, which I hope will demonstrate some of these effects. So let me get this going. Go to here and share screen. And
Voila.
embiggen it. And so you can see that this would correspond to a mode that is not tumbling very rapidly. And as you screen through, you can appreciate that this is showing more motion and yet more motion. And so we need a tool to help us untangle what's going on. And this kind of modeling of motions in this case, a fluid, is relevant to what happens in any material, be it a fluid, a solid, or a gas. So these dynamic considerations play a crucial role in the application of paramagnetic resonance to questions such as the Alzofon experiment.
Well, what about a plasma, though? Does it apply to plasmas as well?
The details of the description would change, but the same considerations are germane, I would say.
Because a plasma sort of like flows like in a movie. It's almost like a single organism.
Still got free electrons.
That's right. It would be the closest to a pure spin system that you could have. But I'm not prepared to go further than that at this time. So let me return to my presentation. And go back to presentation mode. Okay. So The tool of choice is something that's known to spectroscopists as a Hamiltonian, and that basically defines energy levels in the system. So for our purposes, there are a number of interactions in any substance of interest to us as paramagnetic resonance spectroscopists in particular, and those who are interested in leveraging the paramagnetic resonance effect for anti-gravity technology. And the most important one is an energy term describing the interaction of an unpaired electron with an applied magnetic field. That's the S part and the B part. And in addition, there's how those two interact with the local environment. Now, in a gas, this would just be a number, but in a solid or a molecule, the value of G is going to look different depending on which direction you look. For the Alzofon experiments, the other important interaction here is hyperfine, and the same considerations apply. We have the contribution coming from the electron. We also have nuclear magnetic moments that are important, and there's a coupling between the two given by what's known as the hyperfine interaction. And you'll note that this interaction is independent of the magnetic field. So the magnetic field gives us a dial in order to select out the relative contribution of various terms in this Hamiltonian. Now, given all of the microwave toys that Mark has at his disposal, the B field that's relevant here is on the order of 3000 Gauss, or if you're calibrated that way, 0.3 Tesla, which is a substantial field, but it can be achieved by electromagnet technology. That is to say, by pushing current through resistive, or not very resistive, but nevertheless resistive, coil of wire. For a lot of the work that I've been doing, I've been looking at higher magnetic fields. 9 Tesla is typically what I work at. And I have also done experiments at fields as high as 25 Tesla. And if you go to places like Los Alamos, they can do even higher fields. Briefly, they can get explosive compression of magnetic flux lines and get up to, I'm not sure what the latest and greatest figures, but it's something like 40 to 50 Tesla on the order of milliseconds. We can do 9 Tesla for much longer, but as you can perhaps appreciate from looking at these two terms, there's the possibility that you can make the electron Zeeman dominate, or you could crank it way down and have the hyperfine dominate. And this interplay is important in many classes of experiments. Now, just so the nuclei won't feel left out, I want to emphasize that there's another interaction that can be extremely important, and that is the nuclear Zeeman interaction. You'll note over here we have the electron Zeeman interaction. Over here we have nuclear Zeeman. And that is also a field-dependent interaction, but it's written in a slightly different form. Nuclei are localized and tend to be weakly interacting with their surroundings. And so in many cases, a scalar interaction, or rather an interaction that's characterized just by a single number, is sufficient. Remember that up here we said that in a molecule, depending upon what direction you look within the molecule, this value of G can change. And in the classes of experiments that I've been discussing with Mark, we really want to focus on these two interactions, hyperfine and electron Zeeman. These others have effects, but they are typically much smaller, although in many cases it's important to evaluate whether further contributions to the spectrum from this additional term, electron dipole or nuclear quadrupole, are significant. But you'll note that it's only the Zeeman terms that are field dependent. So to drive the point home again, the interplay between these field dependent and field independent interactions give us a dial to tune in interactions of significance and interests. All right, I think I'm going to skip this slide. And now let's focus for a moment on what I'll call the truncated Hamiltonian. I'm only keeping pieces of the electron-Zeeman interaction. I'm only keeping pieces of the hyperfine interaction. So this term and this term define the energy levels that are of interest in the system. And these additional terms affect how the system recovers back to equilibrium once it's been perturbed. And you'll notice that there's this SZIX dependence and this SZIY dependence. And so through the hyperfine interaction, we can actually get magnetization parallel to the nuclear X and Y interactions to talk to the laboratory Z axis. And this is extremely important for the kinds of experiments that Mark wants to do, because it's precisely these mixing type terms that allow for transfer of coherence or transfer of polarization from the electron system to the nuclear system. So although these
Is that what they're talking about in here with the forbidden transitions?
right, so yeah, you won't be able to see that because I've got full screen going.
Right.
And then if I had actually grabbed the correct thumb drive when I came down here, I'd have had a bit more opportunity to present some more relevant slides, but we do the best we can. So let's talk a little bit about frames of reference. We've talked about the laboratory frame, which is defined by the direction of the applied magnetic field. But it's also important to talk about a frame that has as much symmetry of the molecule as possible. And that is known as the principal axis system. And the principal axis system is chosen in such a way to make interactions look simple. For certain values of simple, this is simpler than this, because here all components contribute. So this is what the interaction might look like in the lab system. Here's what it looks like in the principal axis system. And the operator that takes us from the laboratory system to the principal axis system is a rotation operation. And it's complicated, but if you use a sufficiently opaque notation, you can make anything look straightforward and simple. And here's a perfect example of that. There's a lot riding under the hood to get from here to here, but at least in principle, it's fairly well understood what needs to be done. Okay, so here's what a typical frozen system would look like if we were to just measure the absorption across the entire spectrum, where we have say, a cohort of molecules where this NO fragment is aligned along the z-axis. Over here, we have what the spectrum would look like if we had a cohort of atoms, or rather molecules, whose z-axis is parallel to the applied magnetic field. And this is the contributions from the cohort of molecules whose y-axis is parallel to the laboratory z-axis. This in the field is known as a powder pattern, and it arises when all possible orientations of a nucleus are equally like, or molecule in this case, are equally likely. Now, in a solid or a liquid or a gas, there's going to be tumbling of these motions, which we demonstrated earlier in the videos. And so the appearance of the spectrum is going to change. Here's a representation of what the various rotations that contributes to getting from the lab frame to the principal axis system look like. And I'm not sure what I want to say about this. I think what I will say is that you'll remember that I talked about the energy level defining contributions to the system and some kind of broadening contributions. And so those terms that are proportional to SZIZ or SZ and the applied magnetic field define energy levels in the systems. And if I flip the system from spin 1 minus 1/2, nuclear spin plus 1, to electron spin plus 1/2, nuclear spin plus 1, this is what's known in the trade as an allowed EPR transition. And in the spectrum that I've been showing you, there are 3 allowed EPR spectral components which correspond to an electron spin flip. Now, what Mark is interested in is mixing of those allowed levels with contributions from terms such as this, which have magnetization from the IX and the IY direction mixed in as well. And so part of my job as an experimentalist is to help Mark construct a spectrometer that will allow these transitions to be observed, which will allow polarization to be transferred from the electron to the nuclear system, and possibly recreate the experiment that Alzofon did almost 3 decades ago.
1994.
1994. In order to do that, it's extremely important to note that if it fluctuates, it functions. Structure is important, but understanding dynamics can provide insights into mechanisms of function. And this is particularly important for the biophysical problems that I've been looking at, but it's also extremely important for the kinds of experiments that we want to do here. I'm going to leave this up, and the cartoon flowchart is that fluctuating orientations lead to fluctuating transition energies, which lead to line broadening and also bring in these couplings of forbidden transitions that I've been mentioning earlier. This is zooming in on a nuclear spin 3/2 system. It's a little less complicated than the one I was showing before. And here's an example of a time trace of what the fluctuations in energy levels look like for a typical Brownian diffusion trajectory. So as you can perhaps appreciate, as the energy levels fluctuate, the energy in itself is not a particularly well-defined quantity, and the less well-defined it is, the broader the spectrum is going to appear. If we just had two energy levels with no orientation dependence, you would get an extremely sharp line, which can actually be difficult to observe because this magnetic field is too small. This magnetic field is too large. This magnetic field is just right. So you actually have some advantages if there's a little bit of spread in the energy levels. That can make some transitions easier to observe.
And those energy lines that we're seeing, that's reflected RF that we're reading coming out of the chamber. And then we know when it drops that the sample is accepting more energy and that
That's
we reached
right.
the transition, right?
That's right. That's the resonance mechanism. So what you do in a practical experiment is that you tune your resonator so that there is absolutely no reflected wave. Then
We're doing that with the dielectric screw with a little piece of metal on top going
Right,
into
so-
the iris.
so let me bail out from right. So if we can turn this a little bit, you can adjust
Oh, yeah, you can see it.
you can adjust a screw like this to go into and out of this waveguide and adjust it so that there's zero reflection. Now imagine that there's a sample such as that slug of aluminum that Mark was showing earlier. And if EPR resonance occurs, that means that there's absorption in the sample. But when there's absorption in the sample, that means that there's additional absorption in the cavity that you haven't accounted for, which means that the position of this tuning screw is wrong in some sense, and you'll start to see a reflected wave from the cavity.
Oh,
And
it's impedance matching.
Exactly. This is precisely like an impedance matching transformer. And so it's this reflected wave that is what is observed in a classic magnetic resonance experiment.
So those squiggly lines that we're looking at is actually the RF getting reflected back, going through a filtering machine known as a lock-in amplifier. That goes onto an oscilloscope, and we end up with those lines.
And clearly we need a compressor in the background.
Well, that's the moment, yeah.
So let me go back to the show.
Did we just turn that off? I mean, we don't need to turn it.
You can go turn it off. You'll figure out how to turn it off. There's no switch for it. Only on it.
Yeah.
You try to turn it off.
We can pull the plug off. We can just pull the plug out of it, right? It doesn't have a plug inside. Oh, wow. Oh, there we go. There we go. All good. I can still turn it off though.
No, it's fine.
Okay. It won't crank for a while now. So there are experimental considerations that are extremely important. There are theoretical considerations that are extremely important. And for the purposes of my understanding of how relaxation works, I find that kind of a diffusion model is the most relevant one. And in fact, in descriptions of dynamic nuclear orientation, spin diffusion processes play a key role in understanding the relaxation mechanisms that are relevant for a quantitative description of the effect. There are other approaches that you can use, something called a master equation approach. You can also use molecular dynamics. That's how the video of the tumbling box earlier in the tumbling T4 lysozyme molecule were generated earlier. In my hands, at least, the eigenfunction expansion approach of the diffusion model is the most efficient. And of course, we always have to observe that your ideas work in practice, but do they work in theory? I'm not going to say too much more, except to note that it can be important to have a way of translating between a time domain response and its equivalent spectrum. So this is a frequency domain representation of this time domain correlation function. If you take a one-sided Fourier Laplace transform, you will get this spectral information. And there are people who can look directly at the time domain response and know exactly what the frequency domain response is down to the last detail. I hate those people too. So from my perspective, it's often easier to understand what's going on if I can look at the spectral domain as well as the time domain, but both have their place and both are useful. Right, so this is an example of what happens if you melt a spectrum. That is to say, you incorporate more and more motion, you lose details, and what happens is that the line shifts and narrows. And so in a fluid, at least, you get a broad array of line shapes, and it's the details of the line shapes that are key for understanding the precise diffusional model that is relevant. I'm going to skip a lot. And what I will say is some of the work that I've been doing has been extending some of these ideas to instances of what I'll call hindered diffusion and how that affects the possible observed spectrum. And what I've also been trying to do is extend this approach to non-rigid molecules, that we assume basically that everything that we've been modeling is coupled ellipsoids with flexible linkages, but what happens if the ellipsoids themselves are also flexible? And that requires an even deeper level of description. And so to conclude, I'd like to leave you with a suitably absurd image of me in academic regalia playing the bagpipes. And with that, I would be delighted to take any questions that you would care to offer.
I have a few.
I think we need to boost the.
We're not hearing it somehow. I think we're.
Oh, I think.
Can everyone hear us? I can't hear anyone on the chat.
So,
No.
hey, Mark, sorry, guys.
Yeah,
So
we're here.
I was just trying to call Jeremiah. Are you guys all done with your update?
Professor Earle just gave a presentation on EPR, and just pretty much a rundown on what was going on. I think Michael over here
I had a few questions.
in person. Why don't you scoot in there?
Yes, and I was following along with you. I just had to call Jeremiah. In fact, if Michael, if you're going to do a presentation, I'm going to call Jeremiah back real quick.
Oh, no, I'm just gonna ask some questions, but other people can ask first.
Go ahead. You're here in person. You get first dibs.
Oh,
Yeah,
okay.
go for it.
All right. So, I guess, so you have your hyperfine coupling. So, here's one. Have you observed any RF like coupling to the larger structure of the protein? Are there any conformational resonances with proteins and macromolecules in the RF spectrum that you've seen?
So if I were to attach an EPR active moiety at various places in the protein, then at least in principle, I would be more sensitive to the modes that are contributing from a region near the EPR active moiety. And in fact, that's what we do observe. The experiments that I was associated with some years ago now labeled the protein on a highly flexible alpha helix that was fairly short, and also an alpha helix that was longer and more rigid. And we did observe a difference in the dynamics. So even though the EPR active moiety is what we call a reporter group, it is sensitive to the local dynamics of the local environment.
So the transform from the frame of the molecule to the lab frame is different depending on where it's labeled.
Exactly.
So, but have you has that transform ever had an RF response where at certain RF frequencies the transform itself is affected?
In principle, there would be spin torques that would contribute to the spectrum. In our hands, at least, we have not observed an unambiguous spectral signal that could be unambiguously associated with a spin torque term. Basically, the equations of motion that we use are do not incorporate inertial terms. And for our purposes, that's sufficient. There are some applications where inertial terms would be crucial to the success of the experiment, but the formalism that we've found most useful for interpreting our spectra do not require the assumption of a spin torque mechanism.
Okay, cool. So I had another question, but I've forgotten it. So someone else can go next.
I had a couple questions actually. So this one is actually from David Alzofon. He asked me it a while back. Is there any mechanism to measure dynamic nuclear orientation? Can we have a DNO meter or a denometer?
I'm sorry, could you repeat that?
Is there any mechanism that we can directly measure the dynamic nuclear orientation of the nucleus and end up with a dial that's
I mean, you could take the output from the spectrometer and, you know, connect it to a lighthouse if you like, and with sufficient amplification, you could represent it any way you like.
But will the output of the spectrometer tell you how much dynamic nuclear orientation has been achieved, given that we're dealing with a resonance that then translates to another resonance?
What I will
This
say
is like a stepping process.
Right. What I will say in general is that it's much easier to make relative than absolute measurements. And in order to make an absolute measurement of the dynamic nuclear orientation, you would need an extremely well characterized system. And I am reluctant to say more than that because I would need to give it a lot of thought. But those are my unvarnished first impressions.
Okay. Another question was, you've worked in this field for many years now. Have you ever come across anyone looking into this or looking at weight loss in association with regular EPR spectroscopy samples?
Personally, I have not. That doesn't mean that no one has, but I've joined the party only recently, so I can't speak to what someone might have been doing in a lab somewhere else.
Right. Also, I showed you the book. We were reading this earlier, C.D. Jeffries' Dynamic Nuclear Orientation book. Are you familiar with any other books on the subject? Or
There are any number of books that talk around topics that are relevant to this. So for instance, there's a classic textbook by Charlie Schlifter called Principles of Magnetic Resonance that talks about double resonance experiments, the Oberhauser effect. Anatole Abragam has an extremely important book on principles of nuclear magnetism that also talks about double resonance experiments. So in some ways, although the application is new, the technology to get there is mature and extremely well established. So if something is achievable, it should not be a heavy lift. So I'm being optimistic here.
right. In some ways, a lot of the equipment to do this experiment can be quite old, actually.
Oh, yes. It's basically outgrowths of the radiation laboratory at MIT, work that was done during World War II in the 1940s and then written up over the course of the 50s. So that's technology that's almost 70 years old.
Right. So if there is a connection between anti-gravity and EPR, it could well be that they discovered this 70 years ago.
Yeah, if they, well, double resonance methods, let's be a little bit more nuanced. Double resonance methods weren't really discovered until the 50s and didn't attain wide currency until the 60s, I guess. So not quite that long, but
60 years.
at least in principle, yes.
Okay.
I remembered my other, oh no, it's gone again. Someone else can go.
Another question was, what about the spin lattice relaxation time that was discussed in the Alzofon paper, that supposedly aluminum has a longer relaxation time for retention of dynamic nuclear orientation.
Right.
Iron has a shorter one. Like, how does that work? I know it's temperature dependent.
It's a temperature dependent process. I would have to review the mechanism because magnetic resonance of metals is a little bit outside of my research interests and specialty, but I'll get back to you on that.
Okay.
So,
Okay, perfect. Do you remember your question, Michael?
Give me a minute. It'll come back. It was just there again, but no, it'll come back.
We also discussed making a sample that would cool from a liquid state to a solid state within a very strong magnetic field as a way of possibly orienting molecules to an extent that they would make them easier for dynamic nuclear orientation to occur.
Yeah, I think that's a worthwhile experiment to do, but however interested I am in all of these side quests, you've been very good at keeping me on task for my visit here and helping.
Yes, because this is really what we need right now, because we could get all the samples later, but if we don't have this built, it all means nothing. We do have piles and piles of samples. David Alzofon actually contacted me the other day and said, try aluminum, bismuth, aluminum, sandwich them together in the vapor deposition machine. And I'm like, okay, great, we'll try it. We'll call it the David Alzofon variation of the experiment.
So we've sort of been driving the conversation here. Would it be possible for someone else to put a question in the chat?
I think Harold is ready to ask a question. Harold, do you want to unmute?
Yes, I do. Great presentation. A lot of information, a lot of stuff new for me. But the part I would like to ask is, what is the dynamic effect of the gyromagnetic ratio of the sample in achieving, for example, a particular orientation so you can achieve a direction of force controllable? What is, in terms of percentage of all the effect that the gyromagnetic ratio orientation would have on the whole thing?
Well, most samples are going to be diamagnetic, which means that most magnetic effects are very weak. If the sample is strongly paramagnetic, where you have lots of significant nuclear moments and significant unpaired electron moments, then you can have a very large paramagnetic susceptibility, and the observed paramagnetic moment can be quite significant in that case. But maybe I shouldn't downplay or deride the effects of diamagnetic susceptibility. So for instance, in a sufficiently high magnetic field, you can take a little plastic statuette of Mickey Mouse, for example, put it in the bore of the magnet, and it will float due solely to its diamagnetic susceptibility. Another effect that's been observed, and this again is for strongly paramagnetic samples, is that if you take a loose powder and put it in a large magnetic field, then the grains of the paramagnetic sample can themselves align in the magnetic field. And so instead of that broad powder pattern that I demonstrated earlier, you would get a spectrum that is much more reminiscent of a large cohort or a large percentage of the sample that was aligned in one particular direction, that would recapitulate the local symmetry of the molecules. The diamagnetic susceptibility would be along one of the symmetry axes of any needle-shaped, for example, molecular system, and that could be a mechanism for alignment. So it depends, generally speaking, on two things. It depends upon the applied magnetic field for typically a paramagnetic sample, and it also depends in many cases on the temperature. And so the classic experiments, for example, on dynamic nuclear orientation that were done in a magnetic field of about 3000 Gauss or 0.3 Tesla and at liquid helium temperatures. Now, David Alzofon believed that there should be an effect at room temperature if you had an appropriate sample, and his research led him to indicate that aluminum that was doped with a colloidal suspension of iron would be the appropriate thing to try. And in David Alzofon's book, he commented on those experiments, and I've done as deep a dive as I can. It's frustrating in ways because the number of details is not particularly high, but there are a few things that I've gleaned from reading David's commentary on the notebook entries that Alzofon Père, Frederick Alzofon made. So as I said, the goal here is to give Mark an EPR spectrometer that he can then tweak to more successfully do dynamic nuclear orientation experiments, and let's see what we see.
All right. Well, thank you for this very comprehensive explanation. Good one. Thank you.
My pleasure.
Also with by building the waveguide over here and starting to learn about the different resonance nodes, we'll get some practice into what will be in stage 2. You know, if this does work out, we're going to have to make the entire Hall of the Craft into a waveguide resonant chamber, so we can achieve those effects on the entire craft.
Probably need a zero index metamaterial, but that's a whole other story.
The zero index metamaterial is coming right up.
Yeah, because you're going to need to have a very short wavelength. You're going to need a short wavelength along a large craft body, so you're going to need a zero index metamaterial to spread it out across that whole surface.
That's beyond my pay grade at the moment. I'm just a humble EPR spectroscopist, so let's see if we can get a metal cavity to resonate first.
That's a good first step.
Yeah. One step at a time.
So one quick question I had was, so for diamagnetic materials, this effect is smaller, but are there still RF resonances in diamagnetic materials that can be used for nuclear orientation?
Off the top of my head, I can't imagine that there wouldn't be. It's just that in most samples that are prepared for magnetic resonance purposes, it's the paramagnetic component of the susceptibility that's dominant.
Gotcha. And also to clarify, these this paramagnetic resonance it's of a much smaller field strength than, for example, the maximum magnetization of the BH curve. It's much smaller, so it's linearized. Or is that
Generally speaking, yes. Although
for the AC field you're putting in?
Although what I will say is that even in you can still observe conduction electron EPR spectra even in ferromagnets. It's a tiny effect riding on top of the ferromagnetism is just blowing everything else out of the water.
Okay.
But you can still observe it in principle. I believe those experiments do need to be done at low temperature, though.
Okay, yeah, because you get a lot of noise from the lattice.
Yeah.
Phonons and whatnot.
Another question, is dynamic nuclear orientation possible with nuclear magnetic resonance, not EPR, just NMR?
Yeah, that's a good question.
I don't know. I think that you could possibly do a double resonance experiments in the NMR context to look for such an effect. But what I would say is that the electron magnetic moment is typically on the order of 1,000 times larger than the nuclear magnetic moment. So at a given applied magnetic field, at a given temperature, the polarizations that are achievable in the electronic system are roughly three orders of magnitude larger than what's achievable in the nuclear system. And so if you can find a way of efficiently transferring the polarization from the electronic system to the nuclear system, which is essentially the Oberhauser effect, then you're way ahead of the game.
Right. We had a team member, Todd Desiato, who was doing NMR at Earth's magnetic at like half a Gauss, looking for dynamic nuclear orientation effects.
One thing I will say that might be a partial contradiction of that is the fact that in systems with a sufficiently large hyperfine interaction, then it is, or is it hyperfine? I think it is hyperfine, or possibly quadrupolar systems. It is possible to do magnetic resonance experiments in zero field because nature gives you a local magnetic field for free. This is typically, now that I think of it, it's typically found in those systems that have a significant quadrupolar resonance. But there you have energy level splittings that you get for free from the quadrupolar interaction. So
Those are like large molecules.
To do with distilled water. But this is Todd. Hey,
Right.
Hi. In the gravity modification theory, as you were saying about the magnetic field, when you can it gives us a dial to change the magnetic field. And so the effect that I was originally working on with NMR is actually far more pronounced with EPR. So because of the higher frequency. So what I'm getting at is, if the B field, I mean, if you don't really care what frequency it resonates at, as long as your electrons are resonating, then the B field gives you a set energy levels. So a lower B field will have a lower energy level of the resonance. So if you have a gradient in the B field, then these electrons and the molecules they're attached to will have a tendency to walk in that direction toward a lower B field, because that's the direction of lower energy, just like falling in a gravitational field.
Yeah, so that's actually the basis for a lot of magnetic resonance imaging, that you have an applied magnetic field gradient. And you can also do frequency chirp experiments on top of that, and use combinations of both of those techniques to do tomography, to make non-invasive slices through the.
That's how I got into the NMR side of it. And then when Mark introduced me to EPR, I ran the calculations, and because the NMR is in megahertz and the EPR is in gigahertz, that change in energy is much larger for a given gradient in the magnetic field. So it exerts a much larger force on the sample.
There are people who leverage the large gradients that are attainable in, for instance, superconducting magnets to do EPR imaging using the gradient in the magnetic field if you move it out of the center of homogeneity. But what I also know is that if, for example, you were so foolish to leave a steel machinist's scale near the open bore of a 9 Tesla magnet, then there is an extremely significant magnetic force that can act on that steel machinist's scale and suck it right up into the magnet. So that's a kind of magnetic levitation that you never want to have to go to your boss and confess has just happened. Not that it's ever happened to me.
Me neither. But yeah, so but in any case, this is more of than just, it's not so much of a magnetic attraction as it is just a change. It's a force being generated by the gradient in the frequency. So the gradient in the energy of those electrons that are processing. So as the energy, as if there's a tendency for the energy to drop in one particular direction, that's the way they'll want to free fall.
Yeah, well, that's ultimately what's going on, for instance, in the Stern-Gerlach experiment. You rely on
It's Stern? I always called it Stern-Gerlach.
Go ahead.
So yeah, there you take advantage of a field gradient to do spin selection.
Yep.
And that was one of the first kinds of, well, it wasn't exactly a magnetic resonance experiment, but it was one of the important precursors to the development of magnetic resonance technology. But it does rely on steering a beam of atoms or molecules by means of an inhomogeneous field, in this case magnetic.
To determine which was spin up, spin down,
Right.
basically. Yeah.
Yeah. And in terms of the flying saucer that Mark wants to build, if the hull of the ship is in resonance and you control the gradient of the magnetic fields around the circumference, you can control which way the thing will move.
Interesting concept.
Yeah, well,
Maybe you could do
Let's-
90-degree turns at 10,000 miles an hour if you become weightless.
let's see.
It
if we
wouldn't
can
know it. It
levitate.
would just follow the it would just follow the gradient. It wouldn't know it was turning.
Yeah, Ehrenfest's theorem writ large. But let's see if we can levitate a 1.3 gram piece of
Yeah.
aluminum first.
Yes,
Absolutely.
Yes.
Thank you very much. That was a great presentation. I'm gonna have to go back and rewatch that about a dozen times.
Yes, same here too.
Well,
Thanks,
let's do this. Let me put this thing on gallery view. I had forgotten to do this earlier. Everyone, let's give an enormous applause to Mark Sokol and Dr. Kieth Earle
And Michael Perone too.
and Michael Perone.
Thank
Yes,
you.
thank you all for your time. Thank you all so much for your time. Thank you for sharing that. Actually, you guys, I think you guys kind of saved today. We had some major chaos today. So thank you for drilling down in depth on the EPR.
Well, like I tell my students, if we knew what we were doing, it wouldn't be research.